Greetings. We're Team Adams and we'll be covering the basics of software engineering. Part 1. Technical details. Software in the 21st century. It's everywhere. We are now in a time where all of our daily activities are software dependent in some form or fashion. From some of the more obvious things around us, like the apps on our smartphones, or alarm clocks that can be programmed to play a particular song at a particular time, or the smartwatches that are now widely used. We have small software systems in automatic brewing coffee makers, and there are even now smart door locks that can lock and unlock by connecting to our smartphones. Software even invades the aspects of our lives that we pay less attention to. For example, when we pay our electric bill, many of us do that online. Software exists to allow us to set up automatic monthly payments. And software also exists to keep electricity connected to our homes. But just the existence of software isn't where the excitement ends, because while we've come a very long way with software technology already, software engineers are constantly looking for what's better and more efficient. Programming languages are constantly being altered for the better of our systems. Since the year 2000, at least 18 programming languages have come to fruition, including C# and PowerShell. The evolution of software systems. Through software evolution, we have programs that have been developed and then maintained over time. There are plenty of reasons that software evolves. For example, the customer's needs have changed, or they desire new features, or bugs may be found. This is a visual of how software evolves over time. We start with the customer making a request on a program. Then the software engineer has to analyze that request by seeing how it will affect the already present program. Then the software engineer comes up with a feasible solution for the customer's request and creates a release plan. When the solid plan is accepted, the system is updated with the change. Once the system works as expected, the new system is released. And then we start the cycle all over again, because systems and desires and expectations and habits and basically all things in our real world reality don't stay the same. We are constantly in a state of change. Problem solving. The process of analysis. This usually occurs during the release planning stage of software evolution, or during bug fixes. When we analyze, we are breaking down a problem into separate pieces so that we can understand and address each piece individually. For example, if we have hundreds of lines of code, but the code fails, we isolate each function and identify and address the unstable or failing function. Next, we undergo the process of synthesis, which is bringing separate parts together to form a whole. So once we have identified and corrected the failing function in our code, and we have verified that each function or separate section of the program is working correctly, each on their own, we are able to bring each piece back together to reestablish the whole program. While we're problem solving, we use different tools and techniques to be successful. Methods and techniques are basically formal procedures with the expectation to produce some result. Tools are instruments or automated systems for accomplishing something in a better way. Procedures are the combination of the tools and techniques in order to produce the desired product. And the paradigm, well, that's the approach we take to create the product. I've provided my personal cookie recipe here on the right as an example to better grasp the idea of tools and techniques. The tools I use in my recipe are measuring cups and spoons, bowls, sifters, and cookie sheets, etc. My procedure is to mix all ingredients in a particular order. And my paradigm comes with how I mix everything. I use a spoon, not a beater. I make sure that the butter is softened by waiting on the counter overnight instead of in the microwave. And I make sure to finely sift all the dry products before mixing them into the other ingredients. And the same can be applied for other software engineering. We have the problem to solve or some software to create. We develop a plan as to how best we can implement a solution to this problem. Our tools are our computers, efficient programming languages, and the IDEs that work best for us. Our procedure is where we implement our tools and methods on our data in some predetermined fashion. For example, our test plans describe our test procedures. Our paradigm is how we code. Are our comments negligible, or did we write a whole narrative? Did we choose to use object-oriented programming, or did we take a more procedural approach? Ultimately, all of these are used to enhance the quality of our software products. So we look at the problem-solving strategies, but they sound a lot like what we've already learned as computer science students. So what's the difference between software engineering and computer science? Well, from computer science, we acquire the theories and functions of a computer and learn hardware design and how algorithms work. Software engineering uses that knowledge, combines it with the problems produced by the user, and uses the computer as the number one problem-solving tool, producing the tools and techniques used to solve problems. So who is a software engineer? Well, they are computer science professionals that create high-quality software, and they use the principles obtained through computer science and apply it to the customer's problem to come up with a solution. And they view the computer not as the problem, but as their problem-solving tool. But they don't just sit in a cubicle and write code nonstop for hours every day. There are other aspects to the job. They actually spend about half of their time each week devoted to designing and writing code. A survey was conducted by Electric Cloud where it shows that software engineers can spend up to 54% of their time doing other tasks, such as administrative tasks and environment management, and waiting for tests to complete, and waiting for builds to complete, and brainstorming and collaboration. Human errors in software engineering. When systems function, but not exactly as expected. Faults are human mistakes that result in a software design or activity that doesn't match the customer's requirements. And these faults can be seen by the engineer in the code. Often they come from misunderstanding the requirements in the first place. Failures are when there's a departure from the system's required behavior. And this is usually detected by the user because their system isn't working the way they want, or it's not working correctly. Human error can lead to faults, which can lead to failures. But not every fault corresponds directly to a failure. For example, if faulty code is never executed, or if a particular state is never entered, then in theory, it will never crash the code. But there is always the risk of bugs and thus a risk of software failures. There are some forms of software that are considered safety critical. This means that if something goes wrong with the software, it poses a threat to life or health. Safety critical systems or life critical softwares are usually required to have an error rate of 10 to the negative 9. That's a 1 with 7 zeros in front of it. To test that sort of error rate, however, is impossible since a software would need to prove its reliability to have no more than one system failure in 10 to the 9 hours. But 10 to the 9 hours accounts for more than 114,000 years. So that's a bit too long for a test interval. We'll look into how we compensate this problem later on in Chapter 9. And some of the biggest safety critical system failures in history include the failed Therac 25 machines, the potentially dangerous 737 MAX planes, and a recent accident in an Uber self-driving car. The Therac 25 machines are radiation machines used on cancer patients, but there was a software state that was not expected that accidentally left the machine on its maximum power, even after the user switched the machine's power for a lower dose of radiation. The machine eventually was considered defective and removed from practice. In 2018, a 737 MAX plane crashed. Then another in 2019. After that second crash, all 737 MAX planes were downed, either indefinitely or until the problem could be determined and corrected. In 2018, the sensors in the self-driving car owned by Uber that sensed debris or other objects outside the car, it mistook a human riding their bike as something as negligible and allowed that car to run them over. And these are recent incidents. This just comes to show how much further we still have to go in learning and perfecting software technology.
There are a couple different ways to view good quality software. The first is based on the quality of the product. The definition of product quality can vary since different parties are involved with the product in different ways. A couple viewpoints on what product quality is based on are the transcendental view, which is that quality is something that can be recognized but not explicitly defined. The user view, where quality depends on how well it meets the user's needs. The manufacturer view, where quality depends on meeting specifications or requirements. The product view, where quality can be directly related to the inherent characteristics of the product. And the value-based viewpoint, where the quality of the product depends on how much a customer is willing to pay for it. Determining the quality of a product allows you to be compared with other products. External and internal characteristics of what makes a product's quality can be related through models, such as McCall's quality model here to the right, which connects external characteristics such as correctness to internal characteristics such as traceability and completeness. The products used to develop software can also be qualified. This is done by modeling the process, which allows it to be examined to determine how efficient it is at finding faults, building fault tolerance, designing secure systems, and adapting if there's a potentially better process to be used. The process can also be broken down into sub-processes, so individual parts of it can be examined. A good process means a better chance that the finished product will be of high quality. Software quality can also be determined by its business value. Qualifying this focuses on how improving the software will make it more valuable. This business value can be measured through its return on investment. The definition of what return on investment means in the context of software differs between the government and industry. The government definition is dollar-based. It focuses on reducing costs and predicting savings. This is because greater return on investment will result in savings for the government, not contractors. The industry definition is effort-based. It seeks to save time and use fewer people, since reducing effort spent on developing software is important for contractors to gain a competitive edge in the market. Generally, an external view of software quality is a user viewpoint, while an internal view is a developer viewpoint. Users focus on software's ease of use and number of failures it experiences and the severity of them. This viewpoint is based on the user's experience with the product. Developers, on the other hand, have a different approach because they're working from the ground up with the software. They will often have to assess the software before the user even has access to it, and will track faults in requirements, design, and code in order to deliver a working product to the user. Their viewpoint is based on the user's expectations for the software. The three participants in the software process are the customer, the user, and the developer. The customer sponsors development of the software and provides money to the developer. There needs to be clear communication with the customer and the developer in order for the project to be successful. The user is the company, organization, or person who is going to be actually using the finished product. And the developer is the one who builds the system. Since the needs of the customer and the user may differ, it's the developer's job to consider both of them. Defining who actually does software engineering can be complex. Developer teams working on the project can be a variety of sizes. The customer, user, and developer roles can sometimes overlap. For example, a large company with their own software engineering department may develop their own software, combining the customer and developer roles. Or, in a small company, the end user of the software may directly negotiate with and hire the engineering firm, combining the user and customer roles. In other cases, the customer may hire a separate developer, but still be involved somewhat in the development process. For example, if the product is going to integrate commercial off-the-shelf software that the customer has purchased, the customer will be involved with the developer in making decisions about system architecture. And developers can hire other developers or subcontractors to work under them on parts of or the whole project.
There are three main elements of a system. The first element is an activity, which is something that happens in a system, usually described as an event initiated by a trigger. The activity transforms one thing to another by changing a characteristic. This transformation can mean that the data element is moved from one location to another, it's changed from one value to another, or is combined with another data to supply input for yet another activity. The second element involved are called objects or entities. Usually these objects are related to each other in some way. For instance, the objects can be arranged in a table matrix. Often objects are grouped as records, where each record is arranged in a prescribed format. Once entities and activities are defined, we match the entities with the activities. The relationship among entities and activities are clearly and carefully defined. Using these concepts, we can define a system as a collection of things, a set of entities, a set of activities, a description of the relationship among activities and entities and activities, and a definition of the boundaries of the system. Below is an example of a system, with a system boundary, activities, object, and the relationship to each other. You can see a paycheck production system, one that has the activities of data validation, calculation, and printing, that takes input from a computer, does the activities, and then prints out to the mailroom for the paycheck. Next, we'll talk about interrelated systems. An incremental development approach might incorporate a series of stages, each of which frees the previous system from another constraint. An example of incremental development would be if you were creating a new system design. Stage 1 might add a new piece of hardware, Stage 2 might replace the software performing a particular set of functions, and so on, until the system is slowly drawn away from the old software and hardware until it reflects the new system design. In the example below, you can see an incremental development approach on designing, coding, and testing the system, which is done in 3 increments before validation and deployment. This system shows the system components of an interrelated system, which would be the activities, objects, relationship, and system boundaries. In the example below, we can view this system as a collection of systems, each with a special purpose. We can see how the system boundaries separate each subsystem and how together they make up a larger system that is used for water monitoring. As you can see from this system, you can see that it first begins with the smallest subsystem, which is the remote data collection system, which the collection system for remote data builds onto that system, and it continues on until it gets to the reporting system for data, so each system builds on the smaller system to create the larger system, because it's much easier for a software developer to create a smaller system and then build upon that, instead of just having this huge system they must create right away. Next part we'll be talking about is the engineering approach. So there are 9 steps between requirement analysis and definition to maintenance. So requirement analysis and definition first describes the system without knowing the boundaries, the entities, and the activities. Then you have system design, which after the requirements are defined, we create a system design to meet the specified requirements. Then we have program design, which is the phase where the hardware and software resources needed by the program are identified, the logic to be used by the program is determined. Then we have writing the program, which is the phase where the software developer writes the program that meets the system and program design. Afterwards, we have the testing phase, which first starts with unit testing, which after the programs have been written, they are tested at individual pieces of functions, which could be testing objects, testing separate functions before testing everything together. Then we have integration testing, which is once we convinced that each piece works as desired, we put them together and make sure that they work properly when joined with others. Then we have system testing, the final testing phase called system testing, which involves a test of the whole system to make sure that the function and interaction specified initially have been implemented properly. In this phase, the system is compared with the specific requirements. The developer, customer, and user check that the system serves its intended purpose. Then you have system delivery, which is the final product is delivered to the customer. Then you have maintenance, which is the developer organization provides maintenance if anything goes wrong, if its needs or requirements change.
Behind every software project, there's a software development team. That is a team comprised of software engineers that work together to create a new product. And although they might all be software engineers, they might not all be well versed in every role, or they might be very good in every role. And depending on the size of the project, you might have multiple people that fill one role, or you might even have one person that fills every role. The most common roles that you'll find in a development team include but are not limited to a requirements analyst, designers, programmers, testers, trainers, a maintenance team, librarians, a configuration management team, and to some extent even the customer. Because at the end of the day, the customer tells you what all the requirements are, and the product has to meet their needs. And if it doesn't meet their needs, well then all that development time was just wasted. And all these roles work together to complete new products in a timely manner and to the specifications given for the project. Here's what each of those roles do. The requirements analyst works with the customer to develop discrete requirements for a project. Designer works with the analyst to generate a system level description of what the system is meant to do. And the programmers work with the designers to understand the requirements and how to implement the code to meet those requirements. A tester is used to help to catch any faults that the programmers might have missed. Obviously, the programmers should try to find any faults that they can and fix them before moving it on. But the testers are there as like a second layer to make sure everything works right. Trainers all they do is show users how to use the system. The maintenance team fixes faults that are discovered after release and change the product to meet any requirements that might have changed over time. Librarians prepare and store documents used during the life of a system. The configuration management team maintains correspondence amongst all levels of the creation system, which basically means that they're in charge of making sure all of these roles work together to create the project in the best manner possible. And then at the end, like I said, the customer to some extent is part of the development team because they, at the end of the day, decide the requirements of the project, and they work with multiple roles on this team to create the product that at the end they want to be created. Over the past couple of decades, software engineering has changed vastly. It used to be that developers assumed that customers knew what they wanted in a product from the start. And as we see nowadays, this just isn't the case. The customer is part of the development process the whole time, and during any part of that process, they can come back to you and say that they're not happy with the work that you're doing or a certain system that you used inside the project. And because of this, whenever we're creating a project, we have to keep flexibility in mind because, like I said, the customer can change their mind at any step in the process. And that just goes even further with today's systems because they're just so much more complex than what they used to be. Nowadays, most systems do not stand alone. They require interfacing with many other systems to receive and provide information. And as the complexity of the project increases, the number of these systems can increase very fast. And as the number of systems increase, so do the number of connections that are required for communication amongst the systems. And so as the complexity increases, we can see the number of connections in between systems increase exponentially. Also, there's a chance that you might get a piece of hardware from somewhere that you're planning on using in the system, and it turns out that that piece of hardware doesn't work as intended. There's some sort of defect in it. And you have to just work with whatever you're given. You have to be able to change your product however seems fit at any step of the design. Wasserman is a software engineer that is mentioned a lot in this chapter. I tried to find more information on him online, but was not able to locate his first name in the book, so it made research a lot harder. But he has 7 key factors that how software engineering has changed over the decades. The 7 main ones, with number 1 being the criticality of time to market for commercial products. So all these companies are fighting for the same market share, and so the time that it takes you to create a product and get it out to the market can vastly affect this. 2 is shifts in economics of computing, where lower hardware costs and greater development and maintenance costs cause us to maybe get a little bit sloppy, because it's a lot cheaper and easier to just give a system more memory or more computing power than it is to pay a developer more to figure out a way to make it faster or easier. And then number 3 is the availability of powerful desktop computing. As we all know, most of us at home have computers that are more powerful than anything software engineers 30 years ago could have imagined. 4 is extensive local and wide area networking, which is just you're able to, a network is enormous and you have access to it basically wherever you're at nowadays. Number 5 is the availability and adoption of object-oriented technology. 6 is the use of graphical user interfaces using Windows icons, menus, and pointers. And 7 is the unpredictability of the waterfall model, which waterfall model is where you don't begin your work on a project until the part before you is done. And this was used for a very long time in software engineering, and it just is not the most effective way to do it. Being able to assess a problem based on a report from a user, which is referred to as its natural state, can sometimes be difficult or just outright impossible. Because whenever a user submits a report, they might not fully understand the system, and it's hard to figure out what exactly their problem is if their description isn't very detailed about what exactly in the system caused the problem, which normal users usually do not know anything about. So to handle this, we use a concept called abstraction. And an abstraction is a description of a problem that has a level of generalization that allows us to concentrate on the aspects that are causing the problem instead of getting lost in the details. So basically, we dumb down the details to figure out the root of the problem and try to combine things that are alike to help figure it out. Creating an abstraction involves identifying classes of objects that are similar, so you can group them together into a hierarchy. For example, a sensor is a type of electrical device, but sensor is a very broad term. We might have 2 different types of sensors. As you see in the picture, there's a water and an air sensor. And this forms a hierarchy because both of those are sensors, and then all sensors are electrical devices. So you can have this hierarchy to try to help decipher where the problem's at. And also in software engineering, we use a standard notation that's followed that helps to communicate in a group environment. And the analysis and design methods allow us to build models and check them for completeness and consistency, as well as allowing for more reuse of requirements and design components from previous projects, which increases the overall productivity and quality. User interfaces was part of the 7 keys that we talked about earlier. A user interface is part of a system that the user interacts with. For example, if you visit a website, basically everything you see on that home page is part of the user interface. All the buttons and tabs that you might see all activate things on the back end of the code, all with a click of a button, instead of having to interact with a command prompt. It's hard, if not impossible, to design a user interface for a project that you don't have yet, you don't have completed. If you don't have anything If you don't know what the project's going to do or how it's going to act, it's very hard to create a user interface that lets you interact with the backend. To handle this, us software engineers use something called prototyping, which is a small version of a system with limited functionality that is used to help the customer identify key requirements of the system, as well as demonstrate the feasibility of a design or approach. And it shows the user the key functions that are available regardless if they've been fully implemented yet or not. And with system architecture is important for not only the ease of implanting and testing, but also for the speed and effectiveness of maintaining and changing the architecture. An architectural structure of a system should reflect principles of good design, just like in coding. And we will study this more in depth in later chapters. The system's architecture describes a system in terms of a set of architectural units and a map of how the units relate to one another. The more independent the units are, the more modular the architecture is, which allows us to more easily design and develop the pieces separately. As you can see, Wasserman again, he has 5 ways to help partition a system into units better. The first one being modular decomposition, which bases the partitioning on assigning functions to modules. 2 is data-oriented decomposition, which is based on external data structures. 3 is event-oriented decomposition, which is based on events that the system must handle. 4 is outside-in design, which is based on user inputs to the system. And 5 is object-oriented design, which is based on identifying classes of objects and their interrelationships. And the importance of these is allowing us to capitalize on our past projects by reusing both what we have done and what we've learned while doing it. Organization and discipline and the activities of the process of developing software has been acknowledged to contribute to the quality of the software and the speed at which it's been developed. Here you can see a quote from Wasserman again. It goes something like, "The great variations among application types and organizational cultures make it impossible to be prescriptive about the process itself. Thus, it appears that the software process is not fundamental to software engineering in the same way as are abstraction and modularization." And Wasserman said this back in 1996. So, from this, you can see instead, Wasserman suggests that different types of software require different processes to be created, suggesting that an enterprise-wide application will need a great deal of control, whereas individual and departmental applications can take advantage of rapid application development. So as we talked about today, with the different sizes of projects, especially with today's tools, many small and medium-sized systems can be built by 1 or 2 developers that fill multiple roles on the software development team. However, large complex systems need more structure, checks, and balances, and often involve many customers and users, and the development of such systems usually continues over a long period of time.
The figure above shows characteristics of software systems that are of varying sizes. Large, more complex software systems require more structure and management than smaller systems since they have high risk, which is often a result of involving many customers. These systems also require much more rigorous testing and review from other employees, such as a product manager. Meanwhile, smaller systems can be created by a few developers who can take on multiple roles. As shown from the diagram, the software systems at the bottom of the pyramid are smaller and have much slower development and are also less controlled, whereas larger systems are developed faster and are more strictly controlled or managed. While reusing code can be efficient, issues can also arise from this practice. For example, it can be faster to develop a small component of code rather than to search through a very large repository of reusable code. Or issues can also be caused by creating a component general enough to be reused, as it can be much more time-consuming. Also, it can be extremely time-consuming to become familiar with someone else's code and if the quality is up to par. Also, there can often be difficulties documenting the quality and the amount of testing that has been done on these components that are reusable. Also, it can be difficult to document the individual that is responsible if the code is faulty or if it needs to be updated. In order to determine the improvement in software design, a quantifying technique is used. For example, the CEO of Hewlett-Packard, John Young, set a goal of 10 times improvement to quality and productivity for all projects. By using this technique, the improvement between different projects can also be compared. Also, mathematics can be used to solve a problem, look for trends, or characterize a situation using quantifying techniques as shown in the diagram. For example, if you are trying to improve your quality and productivity for a project by 10 times, you'd start out in the real empirical world, and your measurement would be 10 times improvement to quality and productivity. So then you have a formal relational system. And then you can use mathematics and statistics to be able to determine how much improvement, extra time that you need to contribute to be able to reach this goal of 10 times improvement for quality and productivity. How much time it would take you to do that. And then you'd have a numeric result. And then your interpretation would be, if I put so-and-so amount of time and effort into this certain project, then I can reach this 10 times improvement. And then you, based on what the amount of time it takes is, you can implement that into your solution. And that would be how to solve a problem using a quantifying technique. Integrative development environments are tools that can allow for the software development process to be enhanced. During the development process of an IDE, the factors below must be considered. Platform integration involves incorporating different applications and services on one platform. If you've ever used Visual Studio Code before, you can see that because you're able to download many different tools to be able to use them. A different type of integration that needs to be taken into account is presentation integration, where tools can be used through one user interface. Visual Studio Code can also be used to see that. Process integration also needs to be considered, where it is the connection between the tools and the development process. So it's basically the connection between tools and how useful they are for the development process. The following two integration concepts also have to be taken into consideration when developing an IDE. One of these is data integration, which is the ability for tools to share data between one another, and control integration, which is the ability for one tool to inform another tool to perform a specific action. And as shown from the picture below, all the puzzle pieces are being put together to basically develop an IDE. When designing a software system, the quality of code is of immense importance, as we talked about earlier. If it's not, then there could be catastrophic consequences. For example, in 1996, the Ariane 5 rocket, which was run by the European Space Agency, experienced issues maintaining the correct flight path and had to be self-destructed, unfortunately, to avoid the rocket hitting a ground controller. The rocket was carrying 4 satellites, and the cost of the failure ended up being $500 million, and the credibility of the Ariane program was significantly impacted. This tragedy was a result of improperly handled exceptions. After this tragedy, many countries in Europe backed out of supporting the Ariane 5 rocket program as well. To be able to avoid situations of catastrophe, the best software practice is to assume that the software is faulty until extensive testing can demonstrate that it is correct, or at least to ensure that a backup plan is in place in case of failure. As shown in the diagram, this is the Ariane 5 rocket before it was self-destructed. In this case of the Ariane 5 rocket, they did have a backup plan in place, as that was self-destructing the rocket if anything went wrong, but of course that was unfortunately not the most ideal backup plan.
So now we'll be looking at two design examples. In this example, we are looking at an internet banking system. There are three main systems that overall is involved in the internet banking system. The first one is the internet banking system, then email system, and then the mainframe banking system. By this diagram, you can see how the internet banking system works by having several objects such as the web application, single app, page application, mobile app, API application, database, and then you can have you can see the activities of each, such as in the API application provides an internet banking functionality via JSON/HTTPS API, and then we can see the relationship between each. So in the system itself, in the internet banking system, you can see how the relationship works between each object. Web application delivers to the single page application. API application reads from and writes to the database. But you can also see how this system communicates with other systems, such as the API application sending emails using SMTP to the email system and communicating with the mainframe banking system by SML HTTPS. And you can see how all these three systems work together to help the customer have a great banking experience. In our second example, we have a more advanced example of a system that shows clear system boundaries between the environment, service, and product system. You can see how the product system is a part of the entire service system and how they communicate to each other. You can also see all the objects, the activities, the relationship between all three systems. But not all of them have to talk directly to each other, such as in the environment, the product development organizations can speak directly with the product systems without ever speaking with the service system. And in the real world, businesses work like this. Not all the systems talk to each other. Some of them do, some of them don't. But this is a great example of a diagram that shows system boundaries, the objects, and the activities of each.
So from this point on, it's the software engineering lab, and we will be looking at two cases of failures. The first is the state of Florida unemployment system. So the state of Florida has an online unemployment system, but it doesn't meet the standards to provide benefits conveniently and efficiently. Some of the problems that were reported were excessive wait times, numerous glitches, low security. It's hard to navigate the website. So what we can learn from this is to know the system and its relationships. If you had an idea of how this website worked in the unemployment system, you could have a better idea of how to design this system. And also, the customer is not always the user, because in this case, the previous governor, Rick Scott, was the customer for this website, but it shouldn't have been made with the state of Florida in mind. It should have been made with the common person in mind. Another failure is the 911 calls being dropped. Back in early 2014, there was a software glitch that caused emergency services to go out in 7 states. The software error was because of a software requirement. The software requirement was that the phone calls had a preset limit of 40 million, so there could only be 40 million calls that were assigned codes. But after that limit was passed, the system stops taking new calls because those calls didn't have a code assigned to them and they would just get lost. So what can we learn? Even if the solution fits the requirements, it doesn't mean that it's a good quality solution. So from the developer's eyes, they can say, I met the requirement, this is a great solution. But it's not really a good quality solution in the users because it didn't do what it was supposed to do. Here is some of the resources we used for this presentation. This is the continuation of the resources we used. Thank you for viewing our presentation.